Hey everyone, Cassandra Hockman here with Science on Tap of the New River Valley. We're a local organization that's affiliated with the Sigma Xi Scientific Research Honor Society, as well as the Center for Communicating Science at Virginia Tech. Recently, Katie Burke and Susan Chen and I thought we'd ask our community members for questions they might have about the SARS-CoV-2 virus and COVID-19. Our mission is to bring research and researchers and the community together to share ideas and accurate information in a welcoming atmosphere. So to meet that mission, we recently had the really good fortune of talking with Dr. Linsey Marr, now Dr. Kaisen Lin, both experts in airborne transmission in civil and environmental engineering at Virginia Tech. Linsey's expertise has been recently really beneficial to journalists, to engineers, to medical professionals. So she's been serving as an expert in the New York Times, in the Atlantic, Wired Magazine, as well as other news outlets around the country. She and Kaisen have also both been really active on Twitter, working to share information and comment on new as well as archived research about airborne and surface transmission, as well as about filters and masks. In the interview you're about to watch, so I'm glad you're here, Linsey and Kaisen are going to explain what viruses are, how they travel in air and on surfaces, how humidity affects droplets and virus survival, and what their work looks like in the lab. So thank you so much for those of you that have shared questions to guide this interview. We use those to build the questions we asked. So thank you so much for tuning in and enjoy. I just wanted to kind of ask you guys to start maybe telling me a little bit about, you study virus transmission, persistence and spread in air and on surfaces. Can you tell us briefly to you what is a virus?
Yeah, a virus is a small particle. It's about 10 times smaller than bacteria. And they kind of occupy this gray area between whether it's alive or dead. So people kind of debate that. The viruses cannot survive on their own. They need to infect what we call a host cell, and that can be humans. They actually infect other bacteria, they infect plants, they infect animals, and when they infect that cell, they kind of hijack its machinery to make lots of copies of itself that then kind of burst out and spread.
Okay. So how do viruses tend then to live in air or on surfaces?
They can so once they're released from the host into air, or just they can be released in feces and saliva, and then they kind of survive. Some of them are able to survive in the environment for long periods of time, hours, days. Some of them kind of fall apart right away and don't last.
So how do different, from what we've been learning, different surfaces and maybe even different size droplets affect their survival? Can you talk a little bit about how those viruses are deactivated per the size of the droplet, or perhaps what moisture they're in, or what the surface looks like?
So I'll address the question about different surface materials, and then I'll let Kaisen address the question about droplet size and things. Our collaborators at the University of Pittsburgh at Seema Lakdawala's lab has looked at flu virus on different types of surfaces, like silver, it was copper and steel and different types of plastics. And it definitely survives for a long time on steel and plastic, and not as well on copper, which is known to be an antimicrobial type of surface. So that's when we put the virus in droplets on those surfaces and expose them to different conditions.
Yeah. So in terms of how different size of droplet will matter, it's mainly because there are some components in the droplet that inactivate the virus. So let's say there's a droplet and there's not only the virus itself in the droplet, there can also be other like salts and other things, and this component can inactivate the virus with different mechanisms. And with larger size droplet, and the droplets will eventually evaporate in the environment because they're basically exposed to relative dry environment. And then during this process, this component can get concentrated, and the larger droplet basically have higher amount of this component, and with the evaporation, this component can get concentrated and it will cause more virus decay. So that's how basically how droplet size will affect the inactivation effects.
Okay. So what changes if you wipe a counter down with a soap or a chemical alcohol?
Yeah, different chemicals can actually break down the virus. So things like flu virus and the coronavirus have a kind of a lipid envelope, which cells have, kind of this like fatty layer membrane around them. And soaps and detergents are really good at destroying that. And then alcohol, I don't know exactly how it works, but basically you're kind of like physically tearing apart the virus so that it can no longer, you know, infect cells.
Okay. So, can you talk a little bit about the differences in what you know about the flu virus versus the coronavirus, sort of in these in air and surface contexts, or what we know?
Yeah, there's not a lot known right now,
Okay.
but you know, in terms of how the coronavirus survives, sorry, I'm looking over here to another screen I have, which kind of explains this. Yeah, we just don't know a lot right now about how they compare in terms of survival. We know there's differences in how easily they transmit between people and kind of what the health effects are, but in terms of survival, there's just not enough information yet.
Right on. What about? Can you tell us a little about what we know so far about the SARS-CoV-2 virus in terms of its transmission and spread in droplets or on surfaces?
Yeah, there was a study that was just published in the New England Journal of Medicine where they took the virus in the laboratory and they generated these aerosols into a chamber, and they found that they were these kind of very small aerosols that can stay in air, floating around in air for like half an hour, hours or more. The virus is able to survive under those conditions. That was like around room temperature and also at kind of a higher humidity level than what we typically find, like 65%.
Yeah,
Okay.
And then they also looked at the virus, they put it into droplets on they were really pretty large droplets, almost like a small puddle, onto different types of materials. And they looked at steel and plastic and copper. And they found that the virus kind of would last. It slowly kind of decays, like it gradually fades away over several hours. But you know, and they talked about in the aerosols, it survives for at least 3 hours. During that period, some of them are dying off, so they kind of like fade away over time.
Okay. So, do we know then, or do you have a sense of what dispersal might look like in an enclosed space?
Yeah, they should disperse like any other particles, like we think about air pollution particles, dust particles, cigarette smoke. So I've been describing it as kind of like, you know, you see someone smoking, you see that kind of plume dispersing, and that's what's going to happen with viruses in the air too. Of course, those that are in the really larger droplets that are large enough to see, those are going to fall to the ground pretty rapidly. But there's definitely ones that can stay suspended and floating around.
Okay. So I guess the likelihood, or well, do we know much then about how it might spread? Like do we know how much could be ingested to cause some kind of illness?
Yeah, that's a good question. We don't know that yet about how much you need to inhale or transfer from your fingers to your nose in order to cause illness. We know for flu virus, it's, you know, if you can inhale one deep into your lung, that's enough to cause infection, or you might need hundreds if you touch your nose or mouth.
Okay. So are there specific locations where we might be more careful than another? For example, like in a bathroom where there's the hand dryer, and a hand dryer might disperse aerosols more often.
Yeah, you generally want to avoid small confined spaces because levels can kind of build up in there. Just like if there's a smoker around and they're in a small space, you're going to be exposed to a lot more cigarette smoke. As for hand dryers in the bathroom, I think they can blow things around. It can kind of help or hurt depending on what this exact situation is. If you're worried about, oh, you have it on your hands and are you blowing it around using the hand dryer? Well, if you're using the hand dryer, you probably washed your hands. So I wouldn't be concerned about that. I guess I would be concerned, let's say here's where it could be a concern. Let's say you have someone who's sick and standing there coughing and breathing heavily at the hand dryer while they're drying their hands, that the motion of the dryer could blow it or spread it around more in the bathroom than it would otherwise. But at the same time, it also means there's less of a concentrated cloud near the dryer, so the next person who comes along might be exposed to less than otherwise. So it's complicated.
That makes sense. That makes sense. Okay, so this may seem like an obvious question, but then if you're outside, so people that are outside running, particularly, folks that are running behind other folks that are running, it sounds like it probably dissipates in the environment enough that as long as you're kind of keeping that safe, suggested 6 to 8 feet distance, you're probably, relatively okay, right? It's going to disperse kind of around you in a way.
Yeah, I think for outdoor activities, if you're maintaining a distance, that's a good guideline. If I were running and let's say I were following behind the same person for a while, I would probably try to pass them or maybe hang back a little bit or run far off to the side so that I'm not like breathing their exhalations the whole time.
Right on. Okay, that makes sense. So can we talk a little bit about temperature and humidity of viruses generally, I guess, including the coronavirus? So what do we know so far maybe about how it spreads, including how maybe the warmer temperatures in upcoming summer months might affect spread and transmission?
Yeah, that's a complicated question. So with, if it's warmer temperatures in general the viruses kind of decay more. They fall apart, die more at warmer temperatures. In a lot of places, though, we use air conditioning or heating to maintain our indoor temperatures at a pretty constant level. Maybe it's a few degrees warmer in the summertime than the wintertime. So that could certainly help. But there's actually a bigger effect of humidity for fairly complicated reasons. I'll let Kaisen take a crack at that, where you can have differences in survival of a factor of 100 based on swings in humidity. So Kaisen, you want to tackle that?
Yeah, so again, the humidity will, just as I mentioned before, it mainly affect the evaporation kinetic of these aerosols and the droplets. So think about the droplet in a very humid environment. It basically will keep its size. So in this way, the stuff in the harmful stuff for virus in the droplet won't get concentrated a lot. So that will allow the virus to survive well in the humid environment. And then the dry condition, the droplet will evaporate very fast, and then this droplet totally evaporate, completely dried out in a very short time. And we believe that once the droplet completely dried out, virus will maintain its viability. I mean, and then so basically you have virus survive well at low and high relative humidity, but then in the intermediate, like between 40 to 70% RH, then you will find that the droplet evaporate still quite rapidly, but the droplet are able to maintain a little bit of liquid. And at this time, this harmful stuff is there still harmful stuff in the droplet, and then it will affect on the virus and kill them more. So at this intermediate relative humidity range, we have a lot of virus decay. So we basically see a U-shaped pattern in terms of virus viability as a function of RH.
So, Kais, let me ask you, does that mean, so if viruses tend to survive in sort of the extreme ends of humidity, is that right?
Yeah.
And let's say we're in a dry environment, does it tend to kind of go dormant and last longer? Or I guess I'm trying to figure out, like, yeah, how does it survive?
So basically, when viruses survive, I mean, they have their structure not damaged, and once they find a host, like let's say someone else touch the contaminated surface and pick their nose and mouth, this virus, when they get into the whole our respiratory system, they can infect the cells.
Okay.
Yeah.
So how does the environment or the humidity level relate to the surface environment? So in other words, if the virus doesn't actually find a host and it's on a let's say it's on a countertop in a very dry environment versus a countertop in a really humid environment, how might the countertop itself affect the relationship with that humidity?
I think there is a equilibrium between the ambient relative humidity and the countertop. So basically what's the relative humidity in your indoor environment is what's the relative humidity on the surface.
So in other words, they might not have that much of a difference.
Yeah, I mean, in terms of the ambient condition, but the surface material itself will matter when they, as Linsey said, the copper will inactivate the virus faster, and other like plastic and steels, the virus will tend to survive longer.
Right.
Yeah.
Can you tell me a little bit about how you conduct your research, what it looks like in the lab?
Yeah, so we mainly look at relative humidity's effect on virus viability. So first thing we frequently do is to propagate the virus so that they are ready for our experiment. And then the virus are in liquid solutions. And then when we run the experiment, first type of experiment we run is looking at virus viability in aerosols, like small particles can suspend in the air for a long time. So what we do is we use a device called a nebulizer, which can aerosolize the virus from the liquid phase to airborne phase. And then we introduce this virus random aerosols into a drum in which we can control the relative humidity. And then we basically just set our relative humidity inside the drum at a certain level that we're interested in.
Mm-hmm.
So the virus will sit in the drum for a certain period of time. And then we collect the virus sample so that we know if there are any virus survive after certain amount of time, or they all died. And this for aerosols. Then for droplet, we basically just use pipette to spot the droplet on the surface. And then we control the RH, relative humidity, and then compare their survival before and after the period of time. So that's basically how we studied it.
Yeah. So I am curious then, so after you get results from doing that kind of testing,
Mm-hmm.
how do you kind of work to take that knowledge into practical application?
Yeah, so I will start and I will let Linsey to add more. So what we find is that the relative humidity will have effect on the virus viability. As I said, there's a U shape. Mm-hmm. So from the practical side, then maybe we can maintain the indoor relative humidity at that range, like between 40 to 70-ish, to mostly inactive the virus. So that's my implication.
Mm-hmm.
Yeah, so as Kaisen mentioned, kind of humidity control that's the big question, the application of whether that can help reduce spread of flu and maybe colds especially during the winter time. So during the winter time, our indoor humidity is often around 20%, 20 to 30%, in areas where where it's cold outside, and we heat the air, and that ends up resulting in it being pretty dry indoors. So under those conditions, many viruses survive pretty well, respiratory viruses, whether in air or on surfaces. Okay. So the thought is, if our research does pan out, and this is really just one of many different factors that affect transmission, but if this is a big one, then if you can raise the humidity to kind of more of that sweet spot, kind of that Kaisen mentioned, between, let's say, above 40%, below 70%, you don't actually want to get above 60 because that can promote mold growth. But then maybe you would have potentially have an impact on transmission of, let's say, the flu. There was actually a kind of small pilot study that was published last year where they tried this in I think a school or daycare center in Minnesota. They only had 2 classrooms, but they humidified one of them and didn't humidify the other. And they found that I think there were fewer illnesses and maybe less virus found in air and on surfaces in the classroom that was humidified. But there's a lot more research that we need to do before we can really say, oh, that make a recommendation like that.
Okay. Well, I do want to ask you a couple more questions. I know we'll kind of wrap up here soon. Can you tell me a little bit about how like barriers work and how viruses? So we've been thinking a lot about how viruses go airborne. So can you tell me a little bit about what that means for a virus to be airborne, maybe in your work, and then my second part of the question then is how a mask might work to protect or shield from a virus.
So viruses are released into air by coughing, obviously, and sneezing. The viruses are in these respiratory droplets that can range in size from way smaller than we can see to the types of things that we can see. They're also released just by breathing and talking. So there was a study on college students, actually, who had the flu in Maryland, and they came into the lab and they sat there for half an hour and kind of breathed, and then every 10 minutes they had to say the alphabet. Even those who didn't cough were still releasing virus into the air in very small droplets that can stay suspended in air, float around for hours. And so in terms of barriers like masks, the way that they work is that, well, the virus is associated with these tiny droplets, and masks are good at trapping small droplets or particles like dust types of particles, air pollution related particles. And the way they do that is that we often think of a strainer, like you drain your pasta and strain it out, but actually filters work in a slightly different way. So that can work if the particles are huge, but filters can also be very effective for small particles. Because of the way the air flows around the filter fibers, the particles can kind of bump into those fibers. And really small particles have a lot of random motion, just like molecules almost, and that can help them bump into the filter and be removed. So masks, if they're worn correctly, can definitely help. What's not effective is if people wear a mask that has gaping holes on the side, because then you just get short circuiting and the mask isn't really helping much.
Yeah, that makes good sense. Yeah. In the past, I know, Linsey, I've read your op-ed in the Washington Post from 2018, and you have some suggestions on ways to kind of protect yourself from the flu. And I'm curious if you, based on current knowledge of the coronavirus, if there's anything you would suggest that's different, or if we know enough yet to make any kind of recommendations in addition to what we have.
I think the recommendations for flu are similar for the coronavirus, because I think they probably spread in similar ways. Even though the viruses are 2 different viruses, they're both being moving around in respiratory droplets, moving around in the air at least. And how those move around is really determined by the size of the respiratory droplet, and it really has nothing to do with the virus itself. Where the virus itself comes into play is whether it survives well in those droplets that are floating around. And it may be, one of the things that may contribute to the ease of the spread of the coronavirus is that maybe it survives better than flu, but it also could be that maybe it's that people release more of those viruses into the air, or maybe it takes less to cause infection. There's a bunch of different things that could affect how easy it is to transmit.
Yeah, okay. I see. Is there one piece of evidence you think right now that we could stand to gain about the coronavirus?
Yeah, I think that so there have been measurements of kind of whether the virus exists in these very small aerosols that can stay suspended for hours, actually in a study in China. But they only looked at whether the virus is there or not. They did not look at whether the virus was still alive and still could infect. So I think that's the key piece of information. There is a laboratory study, of course, showing that laboratory generated aerosolized virus can survive, but we haven't seen that in the field yet. So I would love to see that kind of data.
Okay. Well, I know we're getting close to time and you all need to go, but I really am so grateful that you have taken the time to talk with us today. And is there anything, do you have any questions for me or anything else you guys would like to add?
No, thanks for this opportunity. We just want to spread good science and help people understand what's going on.
Hey again, everybody. Thanks so much for watching, and especially thanks to Kaisen and Linsey for talking with us. That was really great. We really appreciate the time. We know they're really busy. In fact, despite being busy, I have even contacted them with a follow-up question about how exactly the surfaces make a difference to breaking down the droplets in the viruses. And Kaisen was gracious enough to write me back and say that it's actually the ions and surfaces that interact with what's in the droplet, and so sometimes metals tend to be like copper and silver actually tend to be a little bit more damaging to viruses and even bacteria. So that's how those viruses get inactivated, is it's the ions from the materials of the actual surfaces. So I thought I'd share that with you all. I met Linsey and got familiar with her work for the first time a few years ago when I found out that she actually started studying airborne viral transmission because her son was getting sick from the flu, and she was really kind of trying to figure out how that worked, and she found that there really wasn't much research on that. And so in the process, she started kind of building that research regime, and she has this device she's created in her lab that's this big silver-looking bullet of a drum that they mentioned in the interview that they use to insert, pressure and air, and then they kind of test how the aerosolization happens from there. So I thought I'd share that with you because we have this now really cool body of knowledge that she's contributed to because of that curiosity, as well as her courage in engaging in the public sphere right now. So we've learned to maintain some distance around us even when we're out walking and running because viruses can be transmitted around us in air. And so now we know a little bit about how that works. And if you're actually thinking about making a homemade mask, Linsey has been following the conversation on that and been sharing her thoughts, as well as recent results on what folks are posting, what researchers are doing in that space. In fact, she recently commented on results that show that heavier, densely worn fabrics are more effective at removing particles, droplets, and aerosols. And so she actually suggests skipping that flimsy bandana or scarf and using a heavy pillowcase instead, or even potentially a heavy cotton t-shirt. So thank you again, Linsey and Kaisen, so much for joining us. At some point soon, we'll definitely want to get you your beaker mug for being a Science on Tap speaker. And I'll be sure to figure out with you how to get those to you. But if you're interested, following them on Twitter at Linsey Marr and at Kaisen_Lin. And if you're joining us here for the first time, please feel free to check us out on Facebook, Science on Tap NRV, as well as get on our listserv, scienceontapnrv@gmail.com. We'll be posting soon about other upcoming events, and we also want to give a shout out here to Rising Silo Brewery, who hosts our in-person events on the fourth Thursdays of every month. We'll also be in touch with you guys about when we'll continue those. And so for now, that's all. Thanks so much, everybody, for joining us and for sharing your questions with us. Take good care. Thanks. Bye.